So, what we did last time was we did 6-8, which was the entropy section right here, which was the statistical interpretation of entropy and this stuff right here. Um, so basically, entropy of the system has to be plus the surroundings is equal to the one produced. Remember that. Now, I told you we were moving on, right? We're moving on to the next topic, which is open system energy or entropy rate balance. So what that means is that what we're going to be focusing on now is entropy balance for open systems, which means mass is flowing in and out of the system, right? Which is different than the other one, which was closed systems where some mass is in there and nothing is leaving, right? Not much changes between them. Like this equation is pretty much the same thing as it was before, except this part didn't exist, if you guys recall. This part, it was just these two equations, right? Or these two. Because we didn't have any mass coming in or coming out. So we had to add a term. We added the entropy coming into the system minus the entropy leaving the system. So we didn't really change much, but we did also change one more thing, is that now all of our statements have a dot at the top. And that is because we are now with respect to time. It is a flow rate. So we have an entropy flow rate here. We have entropy accompanied by heat transfer in terms of a rate of time. And then we also have the entropy production per time, right? Or time. So now let's go ahead and get it started. So it says, thus far, the discussion of the entropy balance concept has been restricted to the case of closed systems. In the present section, the entropy balance is extended to control volumes. Like mass and energy, entropy is an extensive property, so it too can be transferred into or out of a control volume by streams of matter. Since this is the principal difference between closed and open systems, the control volume entropy rate balance can be obtained by modifying the closed system one to account for this. So, like I said before, we have changed very little. So right here, this is still rate of entropy change, right? And this is heat transfer entropy, right, coming in. This is entropy coming in from the actual mass coming into the system and leaving. And this is the entropy production by the process. So we didn't change a whole lot. And it says, where dSCV dt represents the time rate of change of entropy within the control volume. The terms MISI and MESE account respectively for the rates of entropy transfer accompanying the mass flow rate into and out of the control volume. Q represents the time rate of heat transfer at the location on the boundary where the instantaneous temperature is Tj. The ratio Q over Tj accounts for the accompanying rate of entropy transfer. The term sigma CV denotes the time rate of entropy production due to irreversibilities. So it didn't really change much. I'm going to skip the integral form of this because it's not really it's not really important for us. So we're going to move on to 610. So 6.9 was all it was introducing this equation, which is the one that you're going to want to know. So this right here, big X. This is the one you want to know. It'll be on your equation sheet as well. And now we're moving on. So it says, since a great many engineering analysis involve control volumes at steady state, it is instructive to list steady state forms of the balances developed for mass, energy, and entropy. At steady state, the conservation of mass principle takes the form of this. So essentially, conservation of mass principle is mass entering has to equal mass exiting, right? We are not losing mass inside. It is staying it's coming into the system and it has to leave the system. And then here's the energy rate balance for steady state. You guys have all seen this. Don't need to go too deep on it. Essentially, it is Q minus W plus the energy coming in, which is through the energy in the fluid, the kinetic energy in the fluid, and the potential energy, right, from the fluid, and then exiting the exact same thing. And then, if we do the steady state form of the entropy rate balance, is obtained by reducing the equation 634, which we saw earlier, and you get this. So now, really fast, you will notice that this went to 0. So the reason why it went to 0 is the following. Because since it's a steady state operation, it means what? Somebody want to, tell me what steady state, why did this go away? Because over here used to be dSCV over dt, if you recall, this one right here. So why did it go away? What happened? So this used to be dSCV over tj right here. Does anybody know? Anybody want to take a shot at why that went away? So, no one wants to take the shot? That's fine. Steady state, if you guys recall, means that no change with time. And so, this right here represented the change of entropy with respect to time. So since there's no change of entropy with time, it operates the same way from second 0 to second 100 or 1,000 or 1 million. This goes to 0. So that's why it takes on the form of this right here. So now we have just Q over T and MI, SI, and ME, SE, and the produced. So this is what we're at. And if you guys recall, these right here are going to be the same. So the mass flow rate will probably end up being the same for most questions. And SE and SI refer to 1 and 2, right? Just so you're aware that these are entropy 1s and 2 at different states. But they give it to you in this form because it's inlet and exit. All right. And then it says mass and energy are conserved quantities, but entropy is not conserved. Equation 4.6 indicates that at steady state, the total rate of mass flow into the control volume equals the total rate of mass flow out of the control volume. Similarly, equation 4.18 indicates that the total rate of energy transfer into the control volume equals the total rate of energy out. However, equation 6.36 requires that the rate at which entropy is transferred out must exceed the rate at which entropy enters. The difference being the rate of entropy production within the control volume due to irreversibilities. So, if you guys recall, entropy production must always be positive, right? You guys would agree with that? If entropy production is positive, that means that this must be true. Because as we go through the process, like this statement must be true, is that if we go through this process, there is going to be heat transfer that accompanies some entropy, but what it means is that essentially the process that you go through always has to add entropy to what came in because of the entropy production term. It always has to add entropy. So does that make sense? Like if we go through a turbine, right, like over here, the point is that the process has to add entropy. And that's due to the entropy production term. So that's what they were saying. So then it says 1 inlet, 1 exit control volumes at steady state. So this right here is what we will be doing mostly. So this will be 1 inlet, 1 exit control volumes. So it says, since many applications involve 1 inlet, 1 exit control volumes at steady state, let us also list the form of the entropy rate balance for this case, which is you reduce the previous equation to end up here. And this is the thing that I changed just a second ago. I said that this would be S1 and S2, and the mass flow rate would be the same. And this is what it reduces to. So what you have now is what I said before, which is just M times S1 minus S2. So M delta S plus sigma plus Q over T represents where we are at now. And then we have here, you can divide by mass and you can separate these things, right? So what they did is they subtracted this to the other side and they divided everything by mass. So what you get is that you get S2 minus S1 is equal to heat transfer per mass times temperature. And then you also get sigma per mass. So this is the entropy produced per mass. So these are just other equations, right? But all it is a difference of dividing out mass. That's it. Nothing has changed, really. And then it says, the two terms on the right-hand side of the equation, 638, denote respectively the rate of entropy transfer accompanying heat transfer and the rate of entropy production within the control volume, each per unit mass flowing through the control volume. From equation 638, it can be concluded that the entropy of a unit of mass passing from one inlet to exit can increase, decrease, or remain the same. Furthermore, because the value of the second term on the right can never be negative, a decrease in the specific entropy from inlet to exit can be realized only when more entropy is transferred out of the control volume accompanying heat transfer than is produced by irreversibilities within the control volume. So, this is important. So earlier we made the note that due to this being positive, if you look at just, if this was not here, let's say Q was not here, S2 is always going to be greater than S1, right? But due to heat transfer, sometimes it might not be. If this is bigger than this right here, like let's say it's like, negative or something, let's say it's bigger, and you move S1 to equal all these things, you could lose entropy because all of it left the system in heat, right? But if it's the opposite way, let's say heat's coming in, you will gain entropy, right? So basically, the biggest determining factors of how entropy is from one state to the next, so like S1 to S2, the biggest factors here are obviously the amount of heat, but not just the amount of heat, the direction of heat. So whether this be positive or negative. That's big for this. And then the other one, which is slightly less, I'm losing the word here, but essentially slightly less important would be the sigma. And the sigma, since it's always positive, it's just a representation of how destructive the process is. If a lot of heat leaves the system, then you might have it to where S2 is less than S1, right? But if a lot of heat enters the system, you will definitely have where S1 is greater than S2, or S2 is greater than S1. So this is where we're at right now. And then it says, when the value of the entropy transfer term is positive, the specific entropy at the exit is greater than the specific entropy at the inlet, whether internal irreversibilities are present or not. That's what I just said. And it says, in the special case when there is no entropy transfer accompanying heat transfer, it reduces to this, which is what it reduced to before. If you guys remember that question we did, this reduced the before the same way. Once Q went away, the difference in entropy is only representative of this term, which is how destructive the process was. Or how much disorder did we add? So we're right here. And then it says, accordingly, when irreversibilities are present within the control volume, the entropy of unit mass increases as it passes from inlet to exit. In the limiting case, in which no irreversibilities are present, the unit mass passes through control volume with no change in entropy. That is, isentropically. So we're back to isentropic. So if no heat leaves, with entropy leaves accompanying heat transfer, and there are no irreversibilities present, you just get S2 is equal to S1, which is equal to an isentropic process. Same as it was before in the control volume. So we're going to do this question here in just a second. So it says, applications of the rate balances to control volumes at steady state. The following example illustrates the use of mass, energy, and entropy balances for the analysis of control volumes at steady state. Carefully note that property relations and property diagrams also play important roles in arriving at solutions. In example 6.6, we evaluate the rate of entropy production within a turbine operating at steady state when there is heat transfer from the turbine. Okay, guys. So this is our question. And these are going to be big in your future in thermodynamic dealings, because this right here is the basis for doing basically all of Thermo 2. So if you want to have a good time in Thermo 2 and not like hate yourself, pay attention here, because there in Thermo 2 there are essentially no more closed systems. It's all open, and it's all stuff like this. So do pay attention. And if you don't pay attention and you get to Thermo 2, I just want you to realize that I did warn you. Fair enough? So let's go ahead and read the question here. So I'm going to pull this to the side, as usual, just so I can get to a certain point here. So it says, actually, I could just do this. Sorry, guys, I'm being dumb. I did this last time. I think this worked way better. I think this is just a way better way of doing this. Wait, why did that not work? Come on, man. Probably because I got rid of it before I used it. Wait, it won't let me paste. Okay. This is going well. Live show. There it is, finally. Alright, so we're there. Sorry about that. Technical difficulties as usual. So, I'll read the question and you guys tell me what we need, what we have. Like, what did they give us? That's where we're going here. So, let's read the question. Let me get back up here. So it says, steam enters a turbine. So let me start the givens column here. So givens. So it says steam enters a turbine, which is water, right? So our working fluid is steam, right? With a pressure of 30 bar. So P1 is equal to 30 bar. Pretty straightforward. And a temperature of 400 degrees C. So we are given that T1 is 400 C. And a velocity of 160 meters per second. So we were just given a velocity, which means that kinetic energy is not going to be neglected. If we were ever given a velocity, it means that you will have to do kinetic energy. So that is what we have so far. Then it says, saturated vapor at 100 degrees C exits with a velocity of 100. So now let's move over here. So we're talking about the second state now. So it says saturated vapor. So what did they just give us there? They gave us the quality. And the quality is what, Tanner? Quality is 1 because we are saturated vapor, right? Tanner is correct. So, and we will draw the diagram in just a second. And you will get used to these because this is how they will look in Thermo 2. We want to spend some time here. And then it says T2. So they said that with a temperature of 100 C. And then we also have a velocity, so V2 of 100 meters per second. And then they gave us some things that are not state-based. They gave us work. So it says at steady state, the turbine develops work equal to 540 kilojoules per kilogram. So they gave us work per mass is equal to 540 kilojoules per kilogram of steam flowing through the turbine. So that is the work. And then it says heat transfer between the turbine and its surroundings occurs at an average outer surface temperature of 350 degrees. So now really fast, what did they just give us? They gave us a temperature, but what did they give us? What type of temperature?
Absolute.
Okay, so they gave us an absolute temperature, I agree, but why did they give us an absolute temperature? What is it going to be used for, is what I'm asking.
The ideal gas.
Don't know about ideal gas. Does anybody else have an idea? So maybe this equation will... so let's do the equations really fast. How about this? So let's do energy balance. The first one, I'm going to do E balance, okay? Is equal to Q minus W, right? So let's do energy balance. Q minus W is equal to M times H1 minus H2. And then it's plus V1 squared minus V2 squared. And this is all over 2, so I know it's going to be hard for me to do, but just bear with me here. Over 2. And then it's also plus G times Z1 minus Z2. Now, obviously, we can get rid of that last part, because we neglected potential energy. So that is the energy balance we're going to use here. Is there any confusion as to how I got this? This is the simple one inlet, one exit entropy or energy balance, okay? And then we also have one more, which is the entropy balance. And the entropy balance was what? So because we're at steady state, right, it said in the question, that means we are 0 is equal to, and this is Q divided by TB plus delta S, which is M times S1 minus S2 plus, I'm going to just type in sigma. So this is sigma, which is entropy produced. So these are the two equations that we're going to use here. And like I said, I highly suggest that you write these out at the beginning. It will help you a lot. So now, would you like to rephrase your statement, Michael? What temperature did we get? It just said heat transfer between the turbine and the surroundings occur at an average outer surface temperature of 350 degrees.
That's going to be our Q loss, right? Q out of the system, which will affect our change in entropy.
Correct. But I'm asking about this temperature here. What is that temperature? It is TB. So essentially think of it this way, is that this heat transfer, it is the boundary temperature, correct. So essentially what it is saying is that our turbine, I'm going to draw a really bad turbine here. Essentially we have inlet, so this will be 1, I don't know the difference between 1 and 2 apparently, so 1, right? Nope. Sorry. I didn't want to shrink that up. So let's do 1 and 2. And then what's happening is that heat transfer between the turbine and its surroundings occurs at an average outer surface temperature. So essentially how this works is that heat is leaving here, right? So we're going to say, so heat is going out. So I'm going to call this Q right here. And what this means is that this is the outer surface temperature. I'm going to draw a little box around it. And essentially this temperature is the outside of the turbine. And so that means heat transfer is going from in here, this hot, because you would imagine a process like this, which has it coming in at 400 Celsius, is going to be really hot inside of here. And you would be correct. Inside of turbines, it's, really hot, boiling hot. And it's leaving the system because, it has to go the opposite, right? Or it has to go hot to cold. So it's leaving the system, and the average temperature of the place it's leaving is 350 degrees Kelvin. So that's the outside of the turbine. This is the boundary temperature of the system. So this is what we're looking at. I know that's a really bad drawing, but we're trying, all right, guys? So let me do this. So now, next up, we have our boundary temperature, which I will put over here. TB is equal to 350 K. And it says, determine the rate at which entropy is produced within the turbine per kilogram of steam flowing in kilojoules per kilogram Kelvin. Neglect the change in potential energy. So those are our marching orders. So here's what we're going to do. We're going to start how we always do with state 1. And I'm going to take volunteers from the audience here. Would anybody like to tell me what we should do about state 1? Find H and S. I agree with you. So now, you can tell that this first state is going to be superheated. And the reason why you can tell is because it's a turbine. And so if it came in at really high pressure and temperature and it comes out as saturated vapor, it means that beforehand it had to be superheated at a higher pressure. So it is going to be superheated. And you'll notice these trends as you use turbines and things like that more often in these questions, but it will be superheated. So we go and we can confirm this at 30 bar. 30 bar is 233.9 degrees right here. This is the saturation temperature corresponding to 30 bar. And as you can see, we are well above that. So we go down and we go find 30 bar, which is Oh, well, of course it's in between lines. Classic. So what we're going to do is I'm going to pick, I'm just going to pick numbers here, or I might just look at the solution to see, like here, because I don't really want to interpolate that. On exams, I'll try not to ever let that happen. But let's see if they do it. So right here, they say that H1 is equal to 3230 from the table. So if you did interpolation using different lines, you would be able to find that. So you were right. We find H1 is equal to 3230 kilojoules per kilogram. And now we have to find S1. So S1, they will also have it in here somewhere, and I will have to go find it really fast. They say that S1 is 6.9212, which is right here from the table. So 6.9212. 6.9212, and this is kilojoules per kilogram. Okay. So state 1 is there. Now we need to find state 2's things, right? So let's do state 2's things. 2. So now state 2. So what do we know about state 2? Well, we know that the quality is 1, and we know that its temperature is 100 degrees Celsius, right? So knowing those two things, we can find these things, right? We can go to the answer because we know that its quality is 1, which eliminates basically anything. It eliminates that we know that it's a Hg value. It's a saturated vapor value right here. Now we just need to go to 100 degrees C and find it. So right here, 100 degrees Celsius, and these are the values we need to grab: saturated vapor of entropy and saturated vapor of enthalpy. So those are the two, and we will grab those as requested. So let's do this. So 7.3549 is entropy, but I'm going to do enthalpy first. Oh, tables, sorry. 2676. This is kilojoules per kilogram. And then S2. This should be H2. H2 is 7 point something, but that's not a good enough answer. 7.3549. 7.3549 kilojoules per kilogram Kelvin. Okay? So now we have found enthalpy and entropy for both state 1 and state 2. So now what we do is we go up to our equations, right? Because once again, these equations dictate what we need to find. So it says that we need to determine the rate at which entropy is produced within the turbine, right? So really fast, so what we need to find is, we need to find this. So entropy balance is here. Our goal for this question is to find sigma. Can you guys see this? Is that it says determine the rate at which entropy is produced, which is the sigma term. This is entropy produced. Right? Entropy produced. So we are trying to find that. Now let's go through this question and see what we know. So we know S1, we know S2, right? We don't need to know the mass flow rate because we're looking at it in terms of mass. If it gave us a mass flow rate or a way to find it, it would tell us that it would be in kilojoules for Kelvin, right? We'd multiply by mass. We do not have that, so therefore this goes away. So we have S1, S2, mass doesn't matter for right now. We were given TB, which means that the only thing left for us to find is Q, right? So can anybody tell me what equation we might use to find Q? The energy balance equation, correct. So we are going to be using this thing to find Q. So now that we know that we need all these other things, right? Now that we know that, let's look at our first equation here. So we don't need to know this right here because it says that potential energy effects are neglected. So this goes away. Do we know V1? We do. It's 160 meters a second. Do we know V2? It is 100 meters per second. So we know those two. Do we know H1? We do. We found it in the tables. Do we know H2? We did. We found it in the tables. Do we know the work? The work was given at 540 kilojoules per kilogram, which means that we can sub this around and find Q. So we will do that real fast. So let's start over here. So let's do this. Reworking the energy balance. So we would do, so we move all this, so work goes over there. So that means you would have Q is then equal to work plus M H1 minus H2 plus V1 squared plus minus V2 squared, sorry, minus V2 squared. And then that's it, divided by 2 over here on the second part. Although I like parentheses this off because I like to treat this as like one quantity. Same for this. So this is where we're at. Now we can plug in our numbers here. So we have Q is then equal to 540 plus. Then we have our enthalpy values, which is a difference of 3230 minus 2676. And this would be plus, I gotta straighten this out a bit, 160 squared minus 100 squared divided by 2. So these are our numbers that we are given. Remember, mass doesn't really matter here because we're getting everything in terms of mass. So you could, the mass, we don't have it. It's just a 1 here, essentially. Or it's not a 1. It's mass goes out. We pull it out. We divide everything by mass. So this is Q per, this will be the Q per mass. So if we do this number, which let me pull out my handy dandy calculator that is here today. Sorry, slamming everything. So we get 3230. But do be careful when you do things like this because you can get things wrong because of how the calculator does it. You just need to be careful. So I got that, which I'm going to say that is wrong. That doesn't make sense to me. I could be, that actually, maybe it does make sense. Minus 100 squared divided by 2. And then it's plus 3230 minus 2676. And then plus 540. So that means that our answer here, which I have as Q is equal to 8894 kilojoules per kilogram. I'm going to go see if that is correct. You know, my calculator sometimes deceives me. Nope, I figured. So this part, what did I do wrong? Oh, it's right. Oh, that's, yep, I mean, that was the mistake. You had to convert this right here. So remember, this is in meters squared per second squared, and to get it to meter, or to get it to kilojoules per kilogram, you have to divide by 2,000 here for SI units. This has to be, it's two times 1,000. Yeah, that makes sense. I was wondering, I was like, man, that seems like a really high number. That's why I checked it the first time. I was like, oh, that doesn't make sense, but I went with it. Divided by 2,000. 7.8. Yeah, okay, this makes a lot more sense. All right. And then we do minus 540. So it looks like my answer is going to be different because of how I rounded things, but I got 21.8. So yeah, they're going to get us something a little bit different, but I got 21.8. So me get rid of this crap. So Q is equal to 21.8. And really fast, you might be wondering, well, wait a minute, if you do this math out, you would find that this would be a positive number here. And you would be correct. So the way I wrote it, I should have had these backwards. And the reason is because if you did this math out, you would realize that this number would be like 500 plus another 540, which would be over 1,000. But I know that I have to subtract it because heat transfer can't come into this system. If the boundary temperature is less than the temperature on the inside, it has to go the other way. So that's how I knew to subtract it. But I should have done that better. I should have illustrated that this should have been flipped. These two quantities should have been flipped. And so this would have been a negative number, and then you would subtract that from this, and you would get this. But I said I should have done better than on that. But hopefully you guys understand that the turbine, because it is hotter than the outside, heat has to leave the turbine. And so if you would have got a positive heat transfer here, that means heat's coming in, and it can't work. So hopefully that makes sense. But yeah, I should have flipped those. It's my fault. And this is kilojoules per kilogram of heat transfer. Although this should be a negative number. I didn't put a negative there, but I'm really nailing it right now, aren't I? So let's do that. Negative 21.8. So now that we have that, we can then move on to our final part. The final part was to use this entropy balance to find the sigma, the amount of entropy produced by the process. So now that we know that, we can do 0 is equal to Q over TB, and this would be plus M, although once again M is kind of going away here. S1 minus S2. And then when we plug our numbers in, we get 0 is equal to negative 21.8 divided by our boundary temperature of 350 Kelvin. Yeah, that's all right. And then plus our S1 minus S2 difference, which is 6.9212. Yeah, I didn't do that one very well. 9212. And this is minus 7.3549. And then plus entropy produced, which is sigma. So what you do is you flip this all around. So essentially it's going to be, to get everything on the other side, the equation will look slightly different. You will have 7.3549 minus 6.9212 in its own quantity. So I moved this to the other side. I multiplied by a negative 1 and you flipped it. And then you move the other one to the other side as well, which would be plus 21.8. 21.8. Oh, wait a minute, that should be subtracted, I'm pretty sure. But we'll see how it works out for now. So minus 350K. So you get this right here. And so when you do this, you get your final answer of sigma. And let me see what I get. So 7.3549 minus 6.9212 plus 21.8 divided by 350. And you get 0.495, basically 496. It's fairly close. So let's go look down here. So right here, you get the answer of 0.49. So, what was my previous answer? Yeah, so we're fairly close here. So, this is how these questions mostly go, is just like this. So you're going to have to find something, use the terms you were given. If you don't have something, you fill it in. You try to find it using some other means. But this is how these questions generally go, whether it be a compressor or a turbine. This is basically how they roll. or even other ones like diffusers and nozzles. You have to do things like this. And so, let me put our sigma answer here. Sorry, I didn't finish the question. Sigma is equal to 0.496, and this is kilojoules per kilogram K. So that is how that answer ended up working out. Now let me see if there's anything left since we did the question. Is there anything left in this chapter? We're probably not going to do that question. Nope. Let me see. Okay, so this chapter is, I mean, there's other questions, but these are, they're like kind of total systems, and we're not really worried about that. But this right here is a heat pump. But that's something that you'll do later. So this right here is something you'll do in chapter 10. You'll do all of these components together in a cycle. But right now, in this class, the furthest we'll ever go is doing this. It'll be one thing at a time. And then maybe in another question you do this at a time, right? But it's never all of them. In the next class, you put it all together. But before we go, there's one more thing I wanted to do. I wanted to draw the TS diagram for this because this is important that we learn that. So let's do the TS diagram. So I'm going to draw this. Well, okay. I'm not going to draw it like that. Not like last time. I have a better idea of how this works. You ready? You guys want to see the expert play right here? This is a pro gamer move. Look at that. Amazing, right? We now have a perfect TS diagram. At least it looks like it. So we have T, and now over here we will have S. So now, for this section, what we are doing is we are working on a turbine. So let's go ahead and draw this little part out. I'll do this as best I can. Okay, so our first thing that it gave us was a pressure of 30 bar. So I'm going to draw the line of constant pressure. Like I said, it doesn't really matter where you do it as long as it sort of looks to scale. Like obviously, it's not going to look perfect because obviously in between each line there's infinitely many lines you can draw. Like you could do 1.01 bar, 1.02 bar, right? You could continue slicing this diagram all the way up in little layers. But as long as it looks okay, it doesn't really matter. So right here is the first line of pressure, and we will call this P1, right? So this is P1. Then down here, we will draw the second line of pressure, which is P2, right? So these represent our two pressures in the cycle, or not in the cycle, in the process. There's only two pressures. There's the one coming in and the one leaving, right? So the one coming in is obviously P1, the one leaving P2. So now where should I draw the first dot? Where should I draw state 1's dot at? Anybody want to take a wild guess where I draw state? Go ahead.
It's going to be superheated, so it's going to be way up there. It's at 400 degrees C.
Yep.
So it's going to be kind of high up compared to on the right side, right? Compared to temperature at state 2.
So I'm going to draw 400 degrees C right here at this line. Because remember, or not 400, that's not 400. That's the saturation temperature, my bad. So let's do that again. Uh-oh. So right here would be the saturation temperature at that pressure. So to do this really accurately, you would have to go in here and you would have to go look up 30 bar and you would say 233.9. So right here, to make this like a really good one, I guess, you would do 233.9, which is the saturation temperature corresponding to these two states right here on this line. The temperature doesn't change. But then we can draw ours up here, right? Which means that we are on that line of temperature, which as you said was 400 C. So this right here is where we are currently, right, on our first state. Now, where is the next one located?
it's right at the boundary of the saturated region and the superheated region down on the second pressure line.
Okay. So you are saying it is something like this, right? So I'm going to try and draw this a little better because it was going to look really bad in the end. So, like I said, not to scale, of course. But essentially, so everybody just make believe that 400 corresponds to this point. You know, use your imagination, or I'd have to redraw it. So how it'll work is the following. Essentially, remember, because this is a TS diagram, this line right here, so I'm going to use a little line here. This line straight down represents the entropy of the first process, right? Straight down here, it's whatever this number corresponds to, which what it corresponds to is the following. It corresponds to our first entropy, which is 6.9.9212, right? And because we went through the process, as you guys see here, our second entropy is 7.35, and he is correct where it ends up. Where it ends up is right here, right on the border, because we were given that the equality is 1. So this right here would be state 2, this one would be state 1. And now, where would we draw this one? Well, you would say right here. So that is the second line of where the entropy is, right? So all the way up. Right on there. And so what we get out of this is the following, is that 7.355. Let's call that. So 7.355. So really quickly, was this process isentropic?
No.
The answer is no. And the reason is why? Why is it not isentropic?
There was a change in entropy.
There was a change in entropy, correct. And you could have known that just from the question. It says heat transfer is coming in, determine the rate of entropy produced. So it is always going to change, right? Because of those two conditions. So this right here is this is not an isentropic process. And how this process looks is, forgive my drawing, but it's going to look something like this. Like a weird arc here, ending down. Something like that. Because it didn't go straight, right? Like that's the whole point, is that it wasn't a straight line down. It was because if it was a straight line down, it would have ended up further into the saturated region, and it would have been isentropic. It is not isentropic here, because we went like this down to state 2, and we gained entropy, right? Because, if you guys recall, from the second law of thermodynamics corollaries, doing this process, there always has to be an accompanying what? Gain of entropy going through a process like a turbine, right? If you guys recall. So this right here was our gain of entropy going through some process like that. It cannot go back this way. The best you can do is isentropic. Right? It's like the Pawn Stars. Best I can do is isentropic. That's the best he can do. So, right here is where we would have been isentropic. Over here is where we were with the actual process. So now, hopefully, this sort of question makes more sense. I can't remember what your homework has in terms of questions. I think you have a turbine, though. But I'm going to go ahead and stop the recording, and we'll look at it in just a second. But hopefully this one made a little bit of sense.